right, thanks for sticking around if people are still here. I am going to take us 50 years, well, 40 years into the future. If I can find my presentation. All right, so in 2019, which is almost 2 years ago by now, which is quite amazing. That is not the presentation that I wanted to share. Can people see that?
Yep, looks good.
I assume so. Okay. So in 2019, the European Space Agency came out with a call for proposals for what they call the Voyage 2050 process. And these things happen very, very rarely. Okay, so there have been so far 2 of them. This is the third. The first one started in 1983. Fun fact, that is when I was born. And so this process these proposals that were put in 1983 resulted in what was then called the Horizon 2000 program. And that is what gave us XMM Newton. After that, there was another call, and that was in 2004, and that was called Cosmic Vision, and that is what is going to give us Athena, but is still not there yet. And now we have the next generation of these opportunity to do proposals for these large missions, and that is this Voyage 2050. This was extremely awkward because, as we know, X-rays can only be done from space, and I am interested in the X-ray side of things. And if you want to have an X-ray thing by 2050, you need to propose now, but we haven't yet seen the results of Athena. So that was a little bit challenging, but we tried to identify sort of what the big discovery field was that was there, that was left. And so we decided to go back to this question of the missing baryons, and we basically decided to propose a very, very, very ambitious mission that would allow you to actually routinely survey warm hot intergalactic medium, CGM, and cluster outskirts. Namely, the specific goal is we want to be able to survey more than 1,000 square degrees, and we want to be sensitive enough that you can look at the outskirts of massive clusters all the way out, not to the virial radius, but to the accretion shock, okay, all the way out to the accretion shock. We want to get L-star halos easily within this survey out to R200C. And we want to find all of the intergalactic large-scale structure filaments that have a temperature above 10 to the 6 K and have an overdensity above 1, which is not an overdensity, right? It's the mean density. And if you look up what you need in order to do all of these things, it turns out that the sensitivity you need to reach, so the dominant emission is coming from 07, 08, and maybe iron 17. These are the strongest lines that you would be looking at if you want to detect all of these things. What you need to reach is a sensitivity of about 10 photons per emission line per degree per night, by which I counted 8 hours, per square meter. So you either need a field of view that is a lot of square degrees or a significant fraction of a square degree, or you need many square meters of effective area, or you need to wait a lot of nights. So what we came up with trying to optimize this is a mirror of about 10 square meters in X-rays, a field of view of about 1 degree. And in addition to this, we would like to have good spectral resolution so that we can actually catch the velocity. So we would like to have an R of about 2,000 to 3,000 resolving power at the lines of interest. And an angular resolution that actually allows you to tell what the structure is that you're looking at. So in terms of the parameter space that we are filling, where there is a big hole, is here. So very high resolving power at the same time as a large grasp. So the grasp is basically like the survey strength. Effective area times field of view. So you see there is really nothing in this corner, and that is what we would like to fill. Okay, I have a couple of technology slides. This is quite challenging to do. if you want a degree field of view and 5 arcsecond resolution, it turns out you need a megapixel detector that is full of TSs. So the people in the lab at SRON tell me that this is not beyond question. It's challenging, but it's not beyond question that we can actually get this done. We can 0.3 EV resolution, I don't have to argue to this audience that we can do, because Lynx is actually planning to have 0.3 EV, but for a small number of pixels. If you want to do this for a megapixel detector, you need to combine things. So you need to combine several ways of multiplexing things. One way is basically multiple absorbers connected to one single TES through different readout channels. And on top of that, so this is one multiplexing, and then you need to apply microwave readout to this multiplexing. So it's 2 layers of multiplexing to reduce the number of readouts that you're going to have. The mirror is actually also very challenging. We weren't, in fact, able to get to 10 square meters, no matter how much I pushed the engineers, but we were able to get to something like 8 square meter, between 6 and 8 square meters. This is with silicon pore optics, what Randall was talking about. And this up here is based on segmented glass foil design. And both of these have so vignetting of 50% at 1 degree radius. 1 degree diameter vignetting of 50%. So it's hard, but it's possible. And if you were to be able to do this, this is what you would get. So this is if you did a survey with the Athena X IFU, which we would not do. But if you did that, you would be able to pick out only these, very, very bright points of the large scale structure. Whereas if you did the survey that we are proposing, you'd actually finally be able to start to see how the cosmic web connects. So how cosmic web filaments connect to the CGM halos. CGM halos connect to cosmic web filaments and to the outskirts of clusters of galaxies. So that was the dream. Before I give the next slide away, the next slide is my final slide. We also thought about some really, really crazy stuff, okay? And so this is what you would do in emission. Of course, you can do very good things in absorption as well if you have 0.3 EV resolution. And so one crazy thing you can do is you can start to detect things in absorption against not bright background objects, but against the cosmic web. So in any part of the sky that you're looking at, you can just add up all of your normal AGN, and you could stack those and you would get the detection of the cosmic web in absorption, combine it with the thing you have in emission. And the other thing you could do is detect the WIM in absorption against clusters of galaxies. So if you have a cluster of galaxies, it shines light from the cluster through a filament. If there happens to be a filament in front of the core of your cluster, you would also be able to detect that in absorption. So this is a little bit kind of out of the box crazy stuff for the 2050s, and I will stop here.
Great, thank you very much.